Okay, we get started today with Turing machines. I think last time before midterm we finished doing mu recursive functions, and so now we explain Turing machines, and then we'll see that. So our first attempt was to capture the idea of computability, and somehow we arrived at mu recursive functions, and we said that Church thesis is basically, we interpreted church thesis as saying that computability is exactly mu recursive functions. And now what we're going to do is we are going to describe an abstract machine that would be equivalent to mu recursive functions, basically. So this would be a different way to view what is computable. And so then we're going to state church thesis once again in this language, in the language of Turing machines. So basically, what is a Turing machine? You might even, so here what we describe is a Turing machine with k tapes. However, the Turing machine with one tape is exactly as powerful as a Turing machine with k many tapes. But and we will prove this equivalence, that k tape Turing machine and one tape Turing machine are basically computing the same class of languages. However, for simplicity, well, simplicity in the sense that not of the definition, but of what we want to achieve with this thing, we describe a more general thing called a k-tape Turing machine. So let's just draw this. You can see there's a drawing here, but let's just redraw this. So what is a k-tape Turing machine? So our signature, there are many equivalent ways to describe this, but the way we describe it is, so you have like k many tapes. So k by k I mean k many. Like it's a natural number. So 1, 2, 3. So let me draw 3 tapes, for example. So this would be 3 tapes. So tape meaning a tape. So it has the cells like this when something can be written. So like this, right? And then all of the tapes are basically infinite, like they go in both directions infinitely in our model. And now you have a tape alphabet, as we had for DFAs and other things. So you have this alphabet A. Let's write it in blue, I don't know. And let's just, for simplicity of our exposition, let's just assume it's 0 and 1, and let's just add couple more symbols that we will always use, which is hashtag, and then this symbol B. This stands for blank. So it it stands for blank, but it's just symbol B. That's all it is. And then you have, so these tape things are written here, maybe something like this, hashtag B, I don't know, 0, 1. Maybe there's something is empty completely, there's nothing written on there, like this, I don't know.
What is the difference between the blank and nothing?
Nothing is nothing, and blank is a symbol B.
White spaces.
Nothing means that there's nothing written on the tape, and B is just a symbol B. We will use it as to represent blank symbols, but as it stands now, the only difference is that this is actually a real symbol B, and there's nothing written here. So it's basically, this is like an empty cell, but B is not an empty cell. It has B on it. Now this is just a trick, nothing else. And so what is your Turing machine? So what your Turing machine is based, so this is 3 tapes, but it might have, so in this case, K equals 3. So I have 3 tapes, but it can be as many as I like. And also, I already said, but let me repeat it again, this is just one tape. If I only have 1 tape, it's the same thing, basically. But I use K tapes because it's easier to then program some things. And then you have one control, finite control, so the head, which is in some state Z. So it has states. So you have alphabet, you have states, and this thing is reading the tape. But it might be reading the tapes on different, so maybe like, so on tape 2 it's here, on tape 1 it's here, and on tape 3, let's say, it's here. So this is like, so it's reading 0, so this is tape 1, so let's call it. So let's call this tape 1, let's call this tape 2, and let's call this tape 3. So on tape 1 it's reading 0, on tape 2 it's reading 1, and on tape 3 it's reading 0. Another way you can, so but the state, it's not in 3 different states, it's just in 1 state. Another way you can imagine it is that, okay, then what it's doing, so let me just first describe what it's supposed to do. So it reads 0, 1, 0, and it will change the state, erase the symbols that it read, overwrite it, and move left, move right, or stay in the same place. This is all it does. So basically what it does, so your delta function, so your transition function will be in state Z, it's reading what? So on tape 1 it's reading 0, on tape 2 it's reading 1, and in tape 3 it's reading 0. So it's reading this. So it's in state Z, it's reading these 3 things. Then what is it supposed to do? It will go to some state, I don't know, Z prime. It might change a state. Then it will overwrite these symbols. That meaning maybe it writes, just for an example, let's take 1, 0, 0. That means it's gonna write 1 here, it's gonna write 0 here, and it's gonna write 0 here. And then it will make a head movement. Meaning, for example, let's make neutral, neutral, well, let's make it neutral, left, and right. This means on tape 1, what this will do is it will erase 0, write 1, and stay on the same place. On tape 2, it will erase, so where is this? It will erase 1, write 0, and move left. That means it will move here. Now it's here. On tape 3, it will erase 0, write 0, meaning, so it erases this, writes 0 again, so it basically does nothing, and moves right. So it will go here. And it will change the state, and now in state Z prime. Okay? It's actually the simplest thing this guy is doing. So if you think of one tape, if it doesn't have, so it just reads this thing, it always erases it, and either writes whatever, it always erases it, writes something, and moves left, right, or stays in the place. So it has 3 movement, neutral, left, right, and things it's doing, and changing the state. But since I have 3 tapes, I have to give you triples, basically. So what it's doing on tape 1, tape 2, tape 3. But as I said already, if you just have 1 tape, it's basically the same thing. So I mean, it's as powerful as the K-tape Turing machine is as powerful as 1 tape Turing machine. You can simulate this K-tape machine on 1 tape machine. Okay, so that's it. That's basically the whole description, and we will treat in a moment what it means when it reads. So basically, what happens when it reads blank things? It can just overwrites them with B, and that's it. But we'll see this in a minute. Here you can see the description. Oh yeah, by the way, I wanted to say this. So there's another way you can think of is, so you have the tapes like this. Again, let's say 2 tapes. So you have, let's say you have 2 tapes like this. And you can think that your machine is basically here, and it's just looking at this thing. It's not moving around on 2 tapes, rather it's always looking at the same place. However, your tapes are moving left and right. It's the same exact description, but I do not use this description because if I say that my head goes right, basically your tape has to move left for a head to go right, and it gets confusing. So what I'm describing, when I say the R, I mean that the head goes right, not the tape moves right. Because if the tape moves right, the head goes left. So in order to avoid this confusion, you can think of it like many different heads, but it's also bad to think of it as many different heads, because then you think, okay, there are many different states, but there is just one state. Finite amount of states, and this thing's here, finite alphabet. So let's give a description, right? Again, finite control with finite set of states, k tapes, infinite on both sides, divided into cells. We did this. Now tape cells can hold symbols for a finite alphabet A, which include a blank symbol B. So we always say that we also always have this blank symbol B. And another assumption we make, that only finitely many cells have non-blank symbols. That means I do not have an infinite input, basically. So I can have infinite many B's because I treat them as blanks. However, only finitely many cells have non-blank symbols. So the real input is finite, because I do not want to take in infinite inputs. And we index each tape from 1 to k, so tape 1, tape 2, tape 3. And for each I, there is a read-write head for tape I, so head that looks here and looks here. And head can read and print symbols from A and make head moves left, neutral, and right. So what is the transition function description, the mathematical description of the transition function? Of course, it's something like this. So for every state and for k tuple of alphabets, so as I described here, so in our case, the k was 3, so we had 3 triple here. So one state and triple. So for what am I reading on each tape? By the way, this is all deterministic. There is no non-determinism going on. This guy makes deterministic movement every time, so it's easier. This is really a function. So for every state and for every k tuple, you produce a new state, you produce a new tuple, the thing you overwrote, and then you make k tuple of movements, left, neutral, or right. So basically, you have a state z. You're reading A1 to AK on tapes, you go to state Z prime, you overwrite C1 to CK, you overwrite A1 with C1, A2 with C2, A3 with C3, and then you make movements. M1 is either L, N, or R. So if M1 is L, you move left on the first tape. If M2 is R, you move right on the second tape. That's it. That's the whole thing with Turing machines, and it describes everything that is computable. That's the idea. And again, you have initial start state, so you're in Z0, you start somewhere, and you have final states, so the end states E. So you start somewhere, you're changing states, reading things, writing things, and then you finally go to some state, and you call this an end state. Okay, then we have to describe what is computation and stuff like this. So what is my Turing machine? Defined mathematically, it's 5 things: states, alphabet, transition function, which is something like this, start state and end state, and we will always assume, this is just for simplicity, nothing else, that 0, 1, blank, and hashtag is always available. So my alphabet, whatever it contains, it always contains 0, 1, B, and hashtag. We will basically only operate with zeros and ones. And hashtag is used to just separate things. So when I have 0110 hashtag 11000, I know that hashtag means that there are basically 2 inputs on one tape. So this is for separation, and B is to represent blank, somehow blank symbols. It's just a symbol for now. It's just B. I can write 0, I can write 1, and I can write B, but I will show you in a minute how this simulates that there is nothing written there. It's like on your hard disk, right? You have a hard disk and your computer is reading it. There's no places on your hard disk with clusters that have nothing on them. They have something, maybe 0, but it's treated as there's no input there. That's what basically this represents intuitively, but okay, there's modifications that we will use quite often, and I want to pay close attention to this. The first modification we will use, that in some cases, your transition function, see what's the difference here between this definition and this definition? For this definition, from every state, whatever you are reading, there is a next step. Because this function has a value for every z and every k tuple, it has a value, the next what it's supposed to do. But sometimes we might define that your transition function is only defined for states which are not final. This means that when your Turing machine goes to a final state, E represents final states, the end states, where your Turing machine goes to an end state, there is no next step. If I define my transition function this way, that now this is not defined for every state, rather all states that are not final, this means that your computer, so your Turing machine is computing, and when it goes to a final state, it has no next step somehow, and it stops. But I might as well define that when it goes to a final state, so the second option is, then what does it do in the final state? It stays in the same state, writes the same symbol, and just keeps, and it's neutral always. So it just keeps on looping at the same point. So when it goes to a final state, it erases the guy, writes the same thing, erases the guy, writes the same thing, so it infinitely continues the computation in one place. I can also say that. I can also ask things like this and things like this, or I can ask nothing and it just goes to a final state and continues to compute. Maybe it moves out of the final state afterwards, I don't care. In this definition. Okay, so let's, actually the best way is to do an example on this, but let's take some conventions beforehand. We will also, I have k many tapes, right? So I will always assume that input is non-blank portion of tape 1. So I will always assume that if I have k tapes, the initial input is written on tape 1. So it's a non-blank portion of tape 1, and I will always assume that the head 1, meaning the first arrow at tape 1, is at the first symbol of the input. So when I start my computation, so all other tapes, so initially every tape is blank. There's nothing written on them other than maybe B's, which I don't care. But let's say they're all blank without even B's. And then I have input on tape 1, and my head 1 is at the first position of tape 1. So this would be my convention. And what is my output, what I will call my output? The output is on a non-blank portion of tape 1, again, and head 1 on the first symbol of the output. Maybe I will need this or maybe not. Ignore this for a moment. So I start my Turing machine with k many tapes. Everything is empty other than there's an input on tape 1. Then I continue doing what am I doing with my delta. This delta is my algorithm. And when I go to the end state, let's say I'm using definition here, then if I go to my end state, I cannot make my next step. And the output, I will call output, is whatever is written on the first tape. So the other tapes are maybe just used for computation. However, I ignore them completely, and the output is just on tape 1. This is just my convention. And let's do the first example here, and maybe copy this. How do I? Window Shift S, maybe. Yes. Let's copy this there, and let's discuss this example in detail. Here. So what is this? This is the machine that adds 1. It takes an input, a binary string, and it outputs add 1. So of course the binary string is just a number, and so it can add 1. So it's incrementing a binary number. So basically this is to go ahead to just basically what this doing is computing the function successor. But for now we're just adding 1. So what is the input? Input is a binary number. So if n is a natural number, bin n is just a binary representation of that natural number. And the output would be binary number n plus 1. Binary representation of n plus 1. And I will call this machine, the name of this machine will be tape 1 equals tape 1 plus 1. This is nothing but the name of this machine. And you will see how this naming scheme is very successful. So this is just the name of the machine. Tape 1 equals tape 1 plus 1, right? So this machine has only one tape. I will only need one tape. Let's read what this thing is doing. So let's look like this. So this only has one tape, doesn't need any K tapes, and it starts like this. Maybe let's make a couple more. And let's say it starts with the binary number 0, 0, 1, 1, 1. And then everything else is this guy's, then we have this blank symbols, whatever. So this, we have not yet demonstrated how configurations work, but this example is a good one to get started. So it starts with the initial state Z0. So it starts like this. So by convention, this is my input. My input is non-black portion of my tape. So this is my input here. And by convention, it's written on tape 1. There's only one tape, no problem. And my head starts here, the input. So in Z0, whatever I read, so this is my program now. For delta Z0A, whatever A is, so A me being 0 or 1, basically, so it's a Boolean. What I do is I stay in the same state, I overwrite the same symbol and move right. So what would be the next step? Oh, that's the only thing that will happen. It will, what really will happen as I did, so it will erase one but then write one again, basically, so it will do nothing. So it will do this and move here. Then it will erase 0, write 0 and move here. It will erase 0, write 0, move here. Let's do this one more time. 1, move here. It will erase 1, and now it's here, but it's still in state Z0, right? Because it stays in the same state. So now it's here, and now it's what's it gonna do next? Again, it's gonna erase 1 here, and now it's on the blank. So it will move here, Z0. So everybody agrees that this will happen, right? But now this was only defined for 0 and 1. So what happens on blank? So when I'm in state Z0 and I'm on a blank, I go to state Q1, overwrite blank again, and move left now. So what will happen, it will move back here, because it has to go left, and it will be in state Q1 now. And it will just erase blank, I don't know, and write blank again. So it will write something like this. So, by the way, the red pen denotes where the machine did something. So how many tapes did it touch? So it touched this guy here, and it's here now. So okay, now I'm in state Q1, so I keep adding. Basically, Q1 means that I'm carrying 1. So in Q1, if I read 0, I go to Q. So let's follow this. So in Q1, if I read 1, I stay in Q1, I change it to 0 and move left. So it will change it to 0 and move left, basically. And now it's in Q1. Now it's going to do the same thing again. It's going to see 1, it's going to change it to 0 again, and again move left, and it's in Q1. And now in Q1, if it sees 0, it changes this to 1 now. It's going to change this to 1. Change the state to Q0. So it's going to go here in Q0. Okay? And in Q0, basically, it does nothing. It goes all the way to the left. It goes all the way to the left in Q0 until it reaches blank. And once it reaches blank, it goes to an accepting state and moves right. So it will go all the way here. It will reach blank. It's going to overwrite blank again, move here, and it will be in an accepting state. And it really incremented it this by 1. So do you see the logic what this guy is doing? You're basically writing a simplest algorithm you can do. So you start, read, go right all the way, and then you have 1 to add, and if you see 0, you add 1. If you see 1, you change it to 0, and you just remember this 1 in Q1 until you reach the point. And if it's all 1s, the only thing that can go bad, if you're still in Q1 and see blank when you're moving from right to left, then you will have to add 1 more 1 and make your thing longer, basically. So this tape will be this thing calculates the successor, basically. So it takes an input, a binary number, and outputs binary number plus 1. So this is, yeah. What if the input was interrupted with blank like this, right? So you're saying if something like this happened, then this would not work. Hence, we make a convention here that input is non-blank portion type. So we make a convention that the input is not interrupted by blank symbols. That's actually a good convention to make. Because otherwise, if you have a blank in the middle, then what is your input? Because which side is your input? What? This machine takes input is just a binary number that is written like this without interruption, and it outputs binary number plus 1. Because I somehow had to interpret what is my input. So if it has hashtags, then what number am I taking as an input? So this then somehow I have to agree that my input is written on tape 1 and it's not interrupted by blanks. It's just like this. Otherwise, my machine might not work, because this program will not work because it's not correctly defined what is the input then. But anyways, this works. You take an input, just a binary number written on tape 1, and it adds 1. And now subtracting 1 is an exercise. So you can do the same exact thing by subtracting 1. You go all the way to the left, maybe, and then do the similar kind of thing. But you can subtract 1, and that would be tape 1 equals tape 1 minus 1. So this thing in blue, let me stress this one more time. The thing in blue is just the name of my machine.
Alright, so what I did, we were like converting blank to 1, right? If it did not fit, if everyone was 1.
Yeah, the leftmost one. See here. So if in Q1, if you reached blank in Q1, then you turn it into 1.
Yeah, but with the minus 1.
Yeah, with the minus 1, you might erase the number and turn it into blank.
Yeah, but like if everyone is 0 and we subtract 1.
Yeah, if everything is 0, you cannot subtract 1 because we're natural. So you might say like
greater than.
Yeah, so maybe subtraction, we can do subtraction like this. So then if you subtract 1, you just keep it at 0. You can think about it. You can also go to negative numbers, of course, there's no problem. But if you want to do this subtraction here, basically, then if you subtract from 0, you should keep it at 0. You might really easily actually check if your input is 0 first and then do things. But anyways, this is just an example of incrementing your tape by 1. But now let's describe the very crucial point of what is a configuration for this thing and what is a computation. And once I describe this, then this will be, whole computer science will fit in 3 lines. So basically, what is a configuration, right? A configuration K, so set of all possible configurations is this. So maybe let's write here. So I will do it for one tape machine, but to do it for more than one tape is an exercise. And as I said, the gist is that if you can do it on one tape Turing machine, then you can do it. If you can do it on K-tape Turing machine, you can do it also on one tape. That is, we will prove this. So one tape Turing machine is powerful enough to program anything you want. This is the church thesis. But basically, so what is a configuration? So configuration is you have this one tape Turing machine. Let's say our alphabet for simplicity again is just 0, 1. Yeah, I also assume blank, and let's say hashtag. And so I have something written here, 0, 1, blank, 1, 1, 0, hashtag, just very general thing. So what is a configuration? And let's say my head stands somewhere here, let's say in state Z. So the configuration basically describes this the status at hand. So basically the configuration here would say, so let's say these things are empty then here, completely empty, not even B's. So it's like this. So the configuration is basically, in this case, 0, 1, B, Z, 1, 1, 0, hashtag, and then let's say it's completely empty. So this is my configuration. So this is just a short way to write this, what I'm drawing every single time. So it indicates what is the string to the left of your head, what is the string to the right of your head. And your state is written at the place showing that, okay, if state is written here, then the first symbol is what the state is looking at. This is the convention. So the configuration is UZV, where U is a string in my alphabet, V is a string in my alphabet. So let's enlarge this. So configuration is UZV, Z is just some state, and V is a string, U is also a string. So it's like, so it's more like Z, I cannot write when it's zoomed in. So in this case, this is V, this is U, and so V1 is basically 1 in this case. So the first thing at V is 1, you can see here. So this is V, this is U, this is Z. So you see what, oh, here it's actually written out, so we can read it. So non-blank part of the tape is substring of UV, right? Head is on V1, meaning that if state is Z is written here, V1 is where the head is located. In this case, V1 is 1. So it's basically writing this down this way. Head is on V1, state is Z. So what is the start configuration now? So this describes the configuration. What the start configuration is when Z, if I have Z0 instead of Z, then it's my start configuration. So for example, here, where was this? So I don't remember what the start configuration was, but it was something that it would be something like Z0, maybe blank here, and then maybe 1 0 1 1 1 0 blank, and maybe then there's empty here. If you play, so here's the first observation. I never touched anything other than 1 blank to the left and 1 blank to the right. So my configuration can be written this way, and it's fine. I might assume that there is nothing written on the tape from the blank to the left and from this blank to the right, and it's okay. Right? So this was my start configuration. The next configuration was, recall, so it stayed in Z0, so the next configuration from this, by the way, let's just go ahead and do this. What was the next configuration? Blank 1 Z0 0 0 1 1 blank, right? This just means what I drew here in the beginning, that it read 1, it changed nothing, basically, so it kept 1, and it moved 1 cell to the right. Then the next configuration was again blank 1 0 Z 0 0 1 1 blank. It's Z0. It always stays in Z0. See, when it's reading anything, it stays in Z0. And at some point, it reaches this. So let's write this. So at some point, it does this, and at some point, it goes here. It goes like blank 1 0 0 1 1 Z0 blank. And what is the next configuration? If it reaches blank with Z0, then it goes to Q1 blank and goes left now. So the configuration will be blank 1 0, 0, 1, Q1, 1 blank. See, it moved to state Q0 and it went left. So it's basically now in Q1 and reading 1. The configuration is just another way of writing this instead of drawing this thing every single time. And the most important thing is how did I know that from here I go here? How did I know this? How do I know what is the next configuration? Yeah. Delta is the one that you write down what delta is. So when you define a Turing machine, it comes with delta. So it defines what is this thing will be called a computation. A computation is the allowed ways from going from one configuration to another one, basically. And this is what we're trying to do now. So again, it says that you have this relation here, right? And here let's look at it. Let's look. This is it. This is the whole computer science, basically wrapped in 3 lines. Everything that can be done this way can be computed. This is the church thesis. So what does this say? So let's say you're in this configuration here. This basically means, let's copy this again. So what does this 3 lines say? So here what I mean is that B is a single letter. So B and A are just single letters. And U and V are strings. So if I will write this part on the picture, on the picture it looks like this. You have B. So let's write. So you have a cell like this. So you have B here, and you have A here. You have something in state Z, and then everything here is written as V, and everything here is written as U. This is what it says. So you have U, then just a single letter B, then you're in state Z, and then A. And the whole thing like this. So you get the point, right? This is just a shorthand for this picture. And now there's 3 things that can happen. By the way, the first assumption that this makes that this B is not empty. Okay, I will use the word blank to mean B, and I will use empty to mean that there's really nothing written here. This assumes that there is something written here and something written here, something written here and something written here. I do not assume that there is an empty space. And I will treat the empty space in a minute, but we'll see in a minute. So let's assume that B and A are really letters. They might be blanks. For example, this might happen, that this is blank. That's okay. I don't care. But there's some A and B. So let's say delta, so I define my Turing machine, and let's say delta ZA is Z prime CL. What this means that the next configuration, so let's check this one first. So what this means that I erased A, I wrote C, and I moved left. So I moved to state Z prime and I moved left. Then my new configuration will be U, Z prime, B, C, V, right? Now what this says is, let's say there was another case that when I'm in state Z, so if I go back to what it was, so there's something like this, so this was, so in second case, the next configuration, I go to state Z prime, I write C again instead of A, but I stay neutral. That means this will be the next configuration. It will just erase this and write C, and this is just U, B, Z prime, C, V. And the other thing I can do, there's only 3 possibilities, is I can go to Z prime, some Z prime, I overwrite C and move right. Then in this case, I will be U, B, C, Z prime, V. That's it. Every program you write for Turing machines is one of these 3. So it's an incredibly simple description of what it means to compute. So basically what it means to compute is you either do this, this, or this. So you right, left, or stay in the place. And but I have to be technical, and let me treat this way, this thing here. So what does this mean? Let's look at it. So let's not draw it again. So what this says that everything on the left side here is completely empty. This, by the way, should answer all your questions about blank. So let's draw this. Let's just draw it. So what this basically says here, the second guy here, is I'm in state Z, I'm reading A, whatever is written here is V, and everything on the left is basically empty, meaning that I completely do not see what's written here. It might be completely empty, so these cells are empty. So there's nothing written there, no blank symbols. And let's say I have to go left. What I do is, so let's say I have a transition function that for Z and A goes to Z prime, write C, and goes left. How will I go left here? What I will do is I will erase this, write C, and I have to go left. And basically when I go left here in Z prime, I just write that there's blank here. I just write B. So this goes into, so let me explain this better. This goes into a definition of computation that when I read A in state Z and I move left, I just wrote B here and that's it. This is a symbol B that I wrote, but I represented emptiness with B. So basically now there will be no difference between empty thing and B. So everything else, if I go right, nothing changes, right? So if I stay at the same place, I just erase A and write C. And if I go right, I jump over C and I go to Z prime. So I erase A, write C, and jump over. And I have to also consider what happens when there's empty things on the right. So this was empty things on the left. What happens if there's empty things on the right? Exactly everything stays the same, other than you have to write B on the right, which is, there's a mistake somewhere here.
There's a small B.
Yeah, here you have to have big B, because if you, no, here it's correct because you go left and this is the same B as here, but if you go right, yeah, if you go right, you write, so you write C, that's okay. So see, what happens when you go right? See, yeah, here is the trick. What happens, so let's say U is on the left, B is on the left, and I'm at Z. So let's draw this. This is also an interesting case. This is really a different case. So this is the case where you have B here, you have U here, and your head is not sitting here. Your head is sitting here, basically. Oh. So basically your head is not watching anything. This is what this thing says. Let's enlarge this. So your head is not looking at anything. And what happens when you go? So basically, how do I act now? I act as if I was reading blank. So if I'm in state Z and so at every single step, what my next action should be, my delta is not defined on empty things. So let me clarify this. Delta something empty is not defined, because delta only takes alphabet symbols here, where epsilon is a string, it's not an alphabet symbol, so this is not defined. So what do I do next? And the answer is, you act like there's blank. So you think, what do I do when I'm in state Z and I read blank? And you do that. So you always substitute emptiness with blank. So
why didn't we do the same thing when we were going left? So
because there was something to read. So when you were going here, right? So there was A to read. So you were in state Z and looking at A. A is just a letter. So the only time you used blank is when you moved left and introduced emptiness, and then you used blank here. Okay, let me explain it better. So let's push it one more stage, and then we go on a break. Okay, there's only, again, the fourth option here, which is completely, what if your configuration is just Z? Meaning the whole tape is completely empty. There is nothing written here. If you think of configuration as something looking at the tape, but let me stress this enough. Let me stress this, that this is just mathematical way to write things. So I'm syntactically defining what it means to have a next step. And if you're Z, you can think of it, there's a state and there's nothing on the tape. What does it mean to go left? What is that you should act like there's a blank. You act like there's B written there. So you read B, whatever your delta tells you, let's say your delta tells you to write C, you write C and go left, you introduce one more B between C and B, basically. And the same exact way, you stay neutral or go right. But now, let me just give you one more assumption, and then there's a break, and you can also ask question, is that, see in our example here, if we go above, you can see that we never touched, where was this? Yeah, I changed it, but when we were incrementing by 1, and I used my red pen, you can see that we never touched this green B or green B. So if you have an input, then your Turing, and if you surround it with enough B's on either sides, somehow you can always consider that this situation never arises. So we will often assume that you have an input and there's enough B's on both sides such that your Turing machine never crosses into emptiness somehow. And if I always assume that this can never happen, this can never happen, and this can never happen because I have enough many little big B's written on both sides, then I can only look at this situation here. And this is what they do, and every computation comes down to this. Okay, let's take a break and you ask questions. Okay, let me reiterate why these three things can be usually disregarded, and only the most important part is this thing here. Somehow why? So let's look at our example. So we had our example here, right? And let's say, so how did we do the adding, right? So let's say we have our tape, and let's say I have my binary number written this way here. And let's say instead of blanks, they are really empty somehow. By the way, I'm drawing these pictures and doing like they're empty and not, but somehow everything was defined syntactically. I mean, there was no pictures and nothing, and the definition kind of gave you all of these things that I'm describing, but I'm, again, just doing this only for the intuition. It's not like there's a real machine and looking at the tape and encountering empty things. No. So basically what happened here is, so I start here with my Z0, and at some point after, 1, 2, 3, 4, 5, 6, however many steps, it came here, right? Cassette player. People actually build Turing machines. You just need a tape and a guy who just looks at one part of the tape and is able to rewrite things. That's all. And there's actually simpler versions of Turing machines, but Turing himself, I think, actually built the real machines and he was doing things with them. Computer is basically a Turing machine. But anyways, let me just go back here. So let's say I want to increment this by 1, and I think I go here with Z0, and after one more step, I come here, right? If I do not write blanks, what I have to do if I do not write blanks is that What is my next step then here? What I have to do, I'm in situation number 3. See, this is my U. So I'm basically in situation 3 now. This is my U. This is my B. And my configuration is U, B, and then Z, right? So this, when I'm adding 1, if I do not write blanks here, as I did before, and they're just really empty, and my input is just written out like this, then I'm in this situation. And what my thing told me is that when I read blank, I have to go back here. So what this tells me is if I'm in this situation, I have to think as if I'm reading blank. So what would be my next step? My next step would be whatever this thing is, Z0 blank. And this by definition was, I don't remember, it was like Q1 blank left. I think this is what it was. So this was written in my Turing machine definition, but if I do not write blank here, I do exactly this. I write blank here, I go here with Q1, and I'm looking at 0. You see what I mean? If there is nothing written here, there is no blank, I just look at this situation arises. But if there was blank to begin with written here, let's say there were blanks written here, then I do not, this situation never arises, and it's this situation. Then instead of A, I just have B, and instead of A, I just plug in B here. So this example should illustrate that if you write enough B's here, you're always in situation 1. Situation 3 only arises because there was nothing here, but it acts as if there's blank there. So there's not really any difference between these two situations. So if you always assume that enough blanks written on the tape so that your head never moves past them to emptiness somehow, then you can always just look at situation 1. So this is just quickly I wanted to say this. So this here is completely describe what it means to have a computation. Okay, let's formally now describe what is computation. So what is so we described this already, but let's formally say this. So you're given a Turing machine, Z, A, delta, Z, 0, E. So 5 things. States, alphabet, transition, your program, where you start and where you end. And say you're given an input, and now we assume that your input is a string in your alphabet that does not contain B. So B is now reserved for empty things, so your input should not contain B's so it doesn't count somehow. So your input is a string in your A without B's. This is what it says. So this is our assumption. So your input does not contain B's. B's are only reserved for blanks. Now, what is a configuration? It's just sequence of configurations. A computation is a sequence of configuration. How do you start? You start in state Z0, and your input is written on your tape. So we're looking at one tape machine at the moment, but it can be done for any tapes. So you have your W written on your tape, you can think of it, and you're in state Z0, and you're basically looking at the first letter of your input. And now I assume that there are many B's written to the right and many B's written to the left. That means if I write enough B's, when this machine starts moving and writing, it will somehow never cross this threshold to emptiness, so it only uses the first definition. This is just for simplicity, nothing else. You can omit this B's, but let's assume that your input is surrounded with enough B's, so your machine never needs to leave this. Now, what is a computation? You start here and then you make the steps by the definitions we just gave. Now, very importantly, so you're making this step, you go from K0 to K1, K2, according to your delta. And now you say that your computation is of finite length T if when you start at K0, go to K1, K2, and there exists some number T, such that when you go to KT, KT is the end configuration, meaning that the state in this configuration is final. So now think of the analogy. What this says that if you're thinking of your machine reading the tape, that it might be reading, it might go to an accepting state and then it might continue, maybe leaves the accepting state, but I don't care. Once it enters the accepting state, I call the string from the beginning to an accepting state as a finite length computation. Somehow I ignore the fact what happens afterwards. And I will say that if this thing exists, such that when I started it at K0 like this on an input, if there exists a configuration where I'm in the end state, I will say that my machine halts. Even though in my head it might not halt and continue to do things, I assume that if it enters the accepting state, it halted. So I will say that my machine halts if such thing exists, the finite string with the end configuration. I will say that if infinite if no such thing exists. So there's no end configuration. So my machine keeps on doing this and it never enters the accepting state. It might happen. I will say that it's an infinite configuration, and M started, and I will maybe say M started with W does not halt. That means it just never enters the accepting state. Okay, let's ignore this canonical. We'll go back to this. So sometimes we will in later lectures, this will become very important when we talk about P equals NP and stuff like this. So tape used is how many tape cells did your machine really visit. For example, what was the tape used in the binary increment machine? It was the length of my binary string plus 2, because it also visited the blank on the right and blank on the left. So the tape used is the length of your input plus the number of tape cells that were visited by your machine during the computation. It can be more than this somehow. Later we will assume more things, but so what will be example of not halting, meaning that the computation that never ends? For example, this. Anything you read, go right. And somehow, let's say Z0 is not an accepting state, so it always stays in the same state and it always goes right. It overwrites A with A again and goes right. Writes A, goes right. Writes A, goes right. So this guy actually has an infinite things. It visits. It keeps on writing blanks after some point, but it never goes to an accepting state if Z0 is not accepting. And so this machine does not halt. Okay, now the question is, so we constructed this. So we gave a computation for one tape Turing machine. Of course, the same exact thing works for K tapes, but you have to just keep track of all possible tapes. So you might say, okay, here you can go left, here you can go right, here you can stay neutral. So you have K many things instead of 3 things. So we will have maybe 3K things. It just gets complicated, but it's the same idea. And the question again is, what can be computed by one tape Turing machine? What is the thing? So we will exactly define what computed means in a moment. Maybe not today, I don't know. So what can be computed by one tape Turing machine? The answer is everything that can be computed at all. And this is known as Church thesis. Because again, we do not have any definition of computability. What we do is exactly say that computable is the thing that is computed by a Turing machine. But in the previous weeks, we said that computable is thing that is computed by mu recursive functions. And we will prove that these two things are the same. Meaning that if it's computed by a Turing machine, it's mu recursive. And if it's mu recursive, you can write a program on Turing machine that computes it. That means that Turing machines and mu recursive functions are the same. And the Church thesis now translates that everything that is computable by a Turing machine. Again, we cannot prove this thing because we do not have the definition. Basically, Church thesis can be thought of as a definition of computability. And we can supply evidence that the evidence will be that many familiar things like, and of course mu recursive functions as well, will be computed by a Turing machine. So now we will just make one more assumption called regularity of a Turing machine. This is just again, just a convention and assumption. It's very nice when you want to compose Turing machines. What is the composition of Turing machine? So let's say for a one-tape Turing machine, composition would be, let's say I have a one Turing machine. It takes an input, and let's say it increments it by 1. So it computes, and takes a binary input and increments it by 1. And let's say then I have another Turing machine that, again, we had 1, that decrements it. The composition will be something like the output of the first machine is an input to the second machine. This is what I want to do, so that first run the first machine and then run the second machine. This is what I'm trying to achieve. And in order to do this, I have to make sure that when the first, for example, I have to make sure that when I finish the computation, the head of the first machine is at the beginning of the output. Then, only then, I can start the second machine exactly at that point. So the regular Turing machine will be a Turing machine which can be composed with a different Turing machine. So for example, I will assume that I will call a Turing machine regular if at the end of the computation, head 1, so if I have many tapes, is at the start of a non-blank portion of tape 1. So basically when I computed something, I moved back all the way and I'm at the start of the output. So this allows me to start a new machine right away. And I will say that tape inscription of tape 1 is not interrupted by bees. Then I will call it regular. So tape 1 actually has an input ready for some other machine. This is again this. And I will assume that all other tapes are empty. So tape 2, tape 3, tape 4 are completely empty. So my regular Turing machine, when I start it, it does something. And when it's finished, the thing is only the first tape is occupied, all other tapes are erased. Whatever is written on first tape is not interrupted by bees, and the head stands on the first cell of the output. ხო, რეგულარი თუ გინდა, ხო. აინახე. So as I said, this is just an assumption. Some Turing machines will be regular, some not. So let's look at very important examples of some Turing machines. So let's look at, so we had this Turing machine called tape 1 equals tape 1 plus 1. So now let's look at a Turing machine called tape 2 equals tape 1. So this is again just the name of a Turing machine, tape 2 equals tape 1. And you tell me what it does. So what it does, it's a 2-tape Turing machine, right? So when it's in state Z0, and it reads A, so it has 2 tapes. So it's in state Z0, it reads A on tape, so A can be 0 or 1, basically. So it reads A, it's 0 or 1, and blank on the second tape, it stays in the same state, writes A, overwrites A with the same thing on first tape, and also writes A on the second tape, and moves right on both tapes. It does this. What happens when it encounters blank and blank on both tapes? It moves to state Z1. Again, it just overwrites both blanks and it moves left. In Z1, whatever it reads on both tapes, it just does nothing. Basically, it overwrites them with the same thing and moves left all the way until it reaches the blanks and goes to an accepting state and moves right. So what does this machine do? Does it? Let's see what it does, actually. What it does, it basically copies tape 1 to tape 2. So it basically what it does, it has 2 tapes like this. So initially the input it's supposed to take is that the second tape is completely empty. So enough B's are written there. And let's say this one contains 1, 0, 1, like this. So first it starts, so my machine is here and it starts, let's say, here and here. So it reads 1, so it reads 1 in blank, right? So it reads 1 in blank, so in state Z0 initially, and it reads, where is it? I lost. So it reads 1 and blank. So it will move, it will write 1, 1 and go right on both sides. So it will erase both of these things, write 1, 1 and go here. And does the same thing again. It writes 0, 0, so it will write 0 basically here. Then it will write 1 here, right? And it will move here, again in Z0. This is what the first line does. It goes right and just copies whatever the first thing was. It writes same thing on the second tape. So now I copied first tape to the second. So okay, what next? I want to make it regular. Well, it's not completely regular in the end, but anyways, I want to move it back here. So what it does if it reads blank, so now when Z0 reads blank on both tapes, blank, 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 it goes to Z1 and moves left. So it goes to Z1 basically, and now it moves back here. And then in Z1, whatever it reads, if it reads the same thing on both tapes, which is always the case, 1, 1, 0, 0, 1, 1, it goes all the way until it reaches blank again. So it goes all the way up to here in Z1. And finally, once it reads blank, blank again, it's here. Then it goes to an accepting state and goes right. So it goes to an accepting state and it goes right. So it's not completely regular in the sense that both tapes are, there's something written on both tapes. However, it's in the end, it's at the beginning of the inscription. What you can do, by the way, is there's an exercise you can do that you can also erase the first tape. So when you're copying from Z0AB, you can go to blank A right? So that will erase the first tape and write it on the second tape. But how this machine here works, it just copies tape 2 equals tape 1. By the way, these names are chosen in a way that they resemble the programming language. Because when you call tape 2 equals tape 1, what you're really doing is you're calling this Turing machine. That tape 2 becomes tape 1. And tape 1 equals tape 1 plus 1 is you just incrementing tape 1. Okay, this is copying tape inscription. Okay, now concatenating tapes encryptions is an exercise. For example, this machine here, tape 1 equals tape 1 hashtag tape 2, what it's supposed to do, it has 2 tapes, something written on tape 1, something written on tape 2, and what it's supposed to do is it's supposed to copy tape 2 and concatenate it with tape 1 and put hashtag in the middle so you exactly know where the separation happens. And you can also do tape 2, tape 1. That means concatenate from the left and concatenate from the right. So this is in your exercise, I guess. Okay. What does this machine do? I mean, the name of this machine is called erase tape 1. Yeah, so in Z0, whatever it reads, it writes blank, goes right. And when it encounters blank, it stays neutral. So it goes to accepting states and stays neutral, but it ends there, it's an accept. So it just erases everything. So we saw that you can add 1, you can copy, you can concatenate, and you can erase. What else can you do? How about, so this is actually a good question to ask. Can I shift the whole thing by 1? So I have a tape inscription, this is my input. How many tapes do I need? 1 tape Turing machine that just shifts the input by 1. How would you do it? Okay, you get the idea. That's actually good. And let's look at the solution. The solution is like this. As many symbols you have, you need basically that many states. So you see, your states are the start state, end state, and then for each symbol, you have to have a state. So if you have symbols 0, 1, hashtag blank, then you have 4 states, but as many symbols as you have to shift, you have state ZA, corresponding state ZA. So when you start your machine, you do not have to go all the way to the right. You start your ZA, and let's say you're reading A, then you go to the state ZA, erase, and go right. So in this case, so it's A can be 0, 1, and hashtag it says, so there's only 3 options. So you go to the corresponding state Z0, but 0 upstairs now, Z1 or Z hashtag, and then when I'm in ZA and reading B, I go to ZB, but I write A because it was memorized in my state. So this is actually the very important. So you do this until you reach the blank, and when you reach blank in state CA, you write A and go to accepting state. And the most important takeaway here is that you can remember finite amount of information in the states. Because you can only have finite amount of states, you cannot have infinite many states. So you can always remember the finite information in your states. So you have for every alphabet symbol, and when you read something, you change the state accordingly to what you read. And there's a unique state that corresponds to what you read. And this is actually a feature of computation. Not of Turing machines, but of computation by Church's thesis. Yeah, this machine is not regular because you do not go back, but whatever. So this was, by the way, this machine is called Shift R tape 1, so Shift right. So you're moving right. There's also Shift left Turing machine on one tape Turing machine. This is an exercise to shift everything left. Okay, now if you understood this one, I'm giving you a string. Write it down on the tape. How would you do it? So I want a Turing machine that just prints something. So the program that says print, and so there's no input, everything is blank, but what your Turing machine is supposed to do, it just writes concrete word down. So it always writes the same word. How would you do it? There's no tape 2. There's one tape Turing machine. There's just one tape, all blanks, and you're supposed to write down a string that I gave you beforehand. So the string is not changing. That's what. So the Turing machine always writes the same string. So it's basically printing number 7, let's say. Yeah, how many states would you need to print? Exactly, yeah, that's the idea. So storing a word W in finite control is your head of your machine, is, let's say your W has length n, then the name of this machine will be tape 1 equals W. So this just writes W on a tape, and what it basically does, it has n states, and the end state is the nth state here. And when it's, so since initial, so my tape was completely blank. When it's in Z0 and it reads blank, it goes to Z1, writes W0 and goes left, or it starts from the left, or what's happening? You can figure it out, but you see exactly what you said. It just prints, so each state now has the word, the letter memorized. So state ZI prints WI. And you have n many states, so Z0 prints W0, Z1 W1, Z2 W3. You print it all the way. You go left, so because you start from, yeah, you go from left to right. So you write your word from left to right in this case, and then you go in the end, and you stay neutral, and this is your end state. Okay, this just prints the word. And what other Turing machines we are constructing here? So what is the head and the tail of so let's first define. Let's say I'm given a binary string. So something like, so let's write it out. So for example, something like this, hashtag 110, hashtag 11, hashtag 0, hashtag 1101. For example, so this is the example of what is written here. So let's say I'm given something like this. So each xi is a string, a binary string, and it just separated by hashtags like this. Why would I need this? Why do I need this? Because this is an input of a function that takes 1, 2, 3, 4, 5 variables. So if this can be thought as natural numbers, you just look at them, what do they represent in binary, and this is an input for a function that takes 1, 2, 3, 4, 5 natural variables. So I just separate them by hashtag. This is why I need my hashtag, so to tell it apart from 0 and 1. But we will see again, as discussed during the break, that you can get rid of the hashtag at all and just use zeros and ones. That's what computers do. But okay, let's say you have something like this. What is the head? So the whole thing here is called x, this whole thing. Head of x is 0, 1, 1, so the first guy, and tail of x is everything else. So x2 up to xr. So the head of this guy here will be 0, 1, 1, and tail will be 1, 1, 0, hashtag 1, 1, hashtag 0, hashtag 1, 1, 0, 1. So this is head, this is tail. And so we can construct a machine that takes input like this, and on tape 2, it just prints the head of whatever was written on tape 1. And I can also construct a machine that on tape 2 prints the tail of tape 1. So it can look at this thing and on tape 2 only copy the first part. It's very easy because you just go copy, copy until you encounter hashtag and then you accept. And in this case, you just ignore, ignore, ignore until you see a hashtag. When you see a hashtag, you go on to a state that starts copying and then start copying. Now, if this was an input of my function of 5 variables, then what this guy is doing is computing a projection basically to the first variable. Let me repeat this again. That's basically it. Okay, we have all this Turing machines here. Oh, okay, so this is the important Turing machine, and it's... By the way, are there any questions on this now? Otherwise, I have to describe a more complicated... Well, this is not really complicated. This is actually very easy, but it's mathematical. So what I want to do, let's first go back here and show you what I want to do. Let's say I have a machine that has k tapes. Let's say it has 4 tapes. Let's say it has 3 because this is only things that I can fit. So let's say my machine, let's use the same exact letters that are used here. So let's copy this. I want to just use the same exact notation. So if we go back here, paste it. Okay, so let's say I have a k-tape machine M. So this guy is called M. And let's say k is 3. So I have a 3-tape machine M. So this machine that operates on 3 tapes. And let's say I have S-tape machine P. Meaning S is smaller than, so S is smaller or equal to K. Meaning, let's say for our example, S is 2. So I have a 2-tape machine. This guy is called P. And let's say this machine is doing something here. And what I want to do is I want to create a 3-tape machine that I will call... So P, let's say 2, 3. So P23 is a 3-tape Turing machine. So it will be a 3-tape Turing machine such that it behaves on tape 2. So let's say this is tape 2, this is tape 3, this is tape 1. So it acts on tape 2 and tape 3 exactly like P and does nothing on tape 1. Is that clear? This is just a notation. Say I'm given a P, which is a 2-tape Turing machine here, so this operates on 2 tapes, then I can create a 3-tape Turing machine, P23, and what does this P23 say? That on tape 2 and tape 3, it exactly acts like P on tape 1 and tape 2. And what I'm supposed to do is I'm going to act like P on tape 2 and tape 3 and do nothing on tape 1. So tape 1 is always fixed, and I'm doing the same exact things that I'm doing on tape 2 and tape 3 according to what P was doing on tape 1 and tape 2. That's basically it. But generally, so what I have is I have a K tape machine, in our case it was 3, and I choose a subset. That means I choose which tapes I want. Let's say if I have a 17 tape Turing machines and I want to act like a 2 tape Turing machine on tape 3 and tape 14. So I choose 3 and 14 here. So I have 17 tapes. Then I choose which tapes I want to imitate on. So some subset here. And then my new machine of P, the subsets that I chose, in my case 2 and 3 were the subsets I chose, will be machine what? So what does this machine do? You can actually, so this machine in state Z, when it reads A, it should act exactly like P on these tapes, and it does nothing on other tapes. That's basically all that's written here. So basically it says that when it's in state Z and it reads A is now a string, it goes to string B, and what is string B? B on tapes that were selected acts exactly like P, and on the movements that were selected acts exactly like P, and on all the other tapes it stays the same. Acts eriak. Let me go back here and you ask questions. Yeah, so I was not recording it, sorry. So the example of this is so you have a 2 tape Turing machine, and tape 1 to 1 basically is a machine that swaps tape 1 and tape 2. So instead, 1, 2 is just does nothing. Just immute. 2, 1 is the idea that whatever was happening on tape 2, it's swapped to tape 1. You can think about this at home. There's nothing complicated going on here. I want to, before we go on a break, I want to give you a interesting definition here. Oh, okay, so I have to do one more thing. Oh, I have to do many more things before I give you the definition I was in. So what is concatenating machines? Let's do this. Let's power through. So what do we mean by concatenating machines? Is exactly what I described for the regular machine. So you start your first machine, and on the output of the first machine, you run the second machine. And I write this machine with name Q equals M semicolon P colon. So this means, so what is machine Q? Machine Q first runs machine M, and then once M is finished, runs machine P on the output of M. How would you implement this? So my question is, okay, let's say I want to do this. What would be the accepting state? Okay, what would be the start state? So what I want to achieve is run machine M. Once it's finished, on the output, I want to run machine P. Exactly. So the start state of Q will be the start state of M. Oh, exactly. So what would be the states of Q? Yeah, the states of Q will be states of M and states of P. The start state of Q will be start state of M. The end states of Q will be end states of P. And now the transition function, this is also very intuitive. Let's say I'm in state Z and I'm reading A. What do? Now, if my state Z was not the end state of M, right? So it's not the end state of M. I do as M would do. If it's an end state of M, I have to go to the start state of P. That's the idea. As we did with DFA. So you have epsilon moves for granted here. So from the end state of M, you always go to the start state of P and do nothing with the letter. And now, if you're in state P, you just do as P would do. That's it. That would simulate M after P. So it will be P after M. And of course, you can do it for as many machines as you like. And now pay close attention. So let's say I'm doing machine M1, I concatenate with M2, M3, then M4, M5, and up to MK. I call this machine that concatenates M1, MK, for I goes from 1 to K, do MI. So this for loop, even though when I'm gonna maybe write a program like for blah, 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 this actually describes a concrete Turing machine. And that's basically what your computer is doing also, just in more layers somehow, that when you write for I equals 1 to K do MI, basically it's just running bunch of Turing machines one after the other. So this blue rectangle is just a shorthand of this thing, which is just a shorthand of doing this K many times. This is just a pseudocode, some of this. And that's just the convention. But I just want to stress this one more time, that this is not some kind of for loop that is implemented in your computer. This is a Turing machine. It's a concrete Turing machine with the name for I want to K, do MI. What is this Turing machine? First you do M1. On the output of M1 you do M2. Then you do M3. How? By this delta functions here. So now we have a bunch of Turing machines. We have tape 1, tape 2, blah, blah, blah. Okay, so now let's look at yet another Turing machine. We do a lot of Turing machine programming, but the name of this Turing machine is this. It's a regular Turing machine, but the name is tape 1 equals 0 question mark. So this Turing machine is supposed to output yes if tape 1 is all zeros, and it's supposed to output no if it's not. So basically it's a check that you do in your programming. So when you write something, if something equals 0, then, so it's the if part. So it's also programmable in Turing machines. How? So what I'm supposed to do is I'm supposed to check whether tape 1 is 0. It's all zeros or not. So but I want to do it regularly, meaning when I check it, I have to go back to the beginning. Hence, I need more states. So I have 1, 2, 3, 4, 5, 6 states. Z0, Z1, yes prime, no prime, yes, no. So these are just the names of my states. So how do I do it? So I start in Z0 and I'm reading A. So I'm checking whether the whole thing is 0. If A is non-zero, so I know already that it is. So I go to state no prime. I write not, so the idea is to not write anything basically. So A stays, so I erase A, write A again and go left. Now if I read 0, I stay in the same state, overwrite 0 with 0 and go right. I have to check the next cell. And I do it all the way so it will go right reading 0, 0, 0, 0, 0, 0. If it encounters non-zero, it will go to no prime, but whatever, until it reaches blank. Once I reach blank, I checked my tape. There's all zeros, so I go to yes prime. Again, I overwrite blank with blank and go left now. The only reason I need no prime and yes prime is I just want to go back. So if my state is yes prime or no prime, so if my state here is yes prime or no prime, whatever I read, I just go left all the way. So I go left, 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 whatever I read until I read blank. And once I read blank, if I'm in yes prime, I write yes. This is my accepting state. And I write no. If I'm no prime, I write no, and this is my accepting state. So basically what this does is it checks whether the thing is all zeros. Why did I need this? Is that I'm able to implement this Turing machine here while tape I is non-zero, do M. So I'm implementing this while loop here, and should we do this? Might as well do this. So first thing I will do is the accepting state here, I will make no an accepting state. Basically, so this I changed my machine such that it only accepts if the tape is non-zero. Okay. So what else? So look at this writing here. What does this say? First of all, this was checking tape 1. I'm telling you that you can check tape I the same exact way. How? You just swap them as we did with before, but so what is Q? It checks is tape I 0. If it goes to an accepting state and the answer is no, then it does M. And what is S? S, whatever it's reading, S, so once you go, so it does M then it concatenates with S, and S just goes back to the beginning of this guy here. So basically you see that it's a while, but it's very good so this is a K-tape Turing machine, checks tape I. So tape I equals 0 is a K-tape Turing machine that is tape 1 equals 0 on tape I, and it does nothing on other tapes. Then S just connects the end of M to the start of tape I equals 0. So it checks, is tape I 0? No, does M. Is tape I 0? No, does M again. And if tape I is 0, then it returns yes. Yes is not my accepting state, so it will not do M anymore. So it's exactly what we described. It is a while loop that until tape I is non-zero, it does M. And this is actually a good point to end perfectly. Then we discuss everything else tomorrow, right?